Okay, before we get started, so good morning, everybody. Welcome back to Math 115. So today we're going to continue our review by looking at this final exam. I think we're down to 3 students in person. Oh no, here's some more. We got 5. Share the screen. Yeah, good morning. Yeah, I got my coffee here. I drank way too much coffee yesterday, though, and then I couldn't fall asleep last night. Let's see here. I think there's some feedback coming through from somebody's mic. Maybe, I think that might be Sam. Could you go ahead and mute your mic for me? Thank you. Today is not our last lecture. Today is our second to last lecture, as far as I know. I think we have one on Monday, but let me look at the schedule to actually be able to, oh, never mind, Blackboard is down. Okay, I can do this. I know where this is. There it is. Yeah, we have one class on Monday. So one final review on Monday. And then nothing until the final on May 4th. Okay, so, oh, this is something else. Here we go. All right, before we start, let me poll the class. Anything that anybody wants to talk about in today's review session, or shall I just go ahead and continue on with this thing here? If anybody has anything that they want to discuss, I can try to find problems within these practice exams that suit that need, or I can try to come up with some on the spot or find some in the book, or I can just kind of lecture on a given topic for a little while if anybody has anything that they want to discuss. So for example, if you were reviewing your homeworks and you were going back and you found that all of the homework that we did from chapter 1 on like transformations of functions, you couldn't reproduce your results, then you know, maybe you would say, hey, I was struggling with transformations of functions. Can we talk about that? And I could go through some of that stuff. Or if you just felt that one particular section of the class was the one that was the hardest for you. Okay. Doesn't really seem like there's anything coming in, but that's okay. If you think of anything later on, you can put it in there, and I'll do my best to address it. Okay. Happy Earth Day, by the way. I'm pretty sure today's Earth Day. Isn't it? Yeah, today's Earth Day. Happy Earth Day. Okay, well, we're going to jump right in and do some of these problems then. So I'll start off with this simplification problem. So what do we got? We got 2 rational expressions. Okay, I call each of these guys that is in a purple box, I call that a rational expression because it's a ratio. Okay, it's a ratio of 2 polynomials. Okay, so if the numerator is a polynomial and the denominator is a polynomial, then we call this a rational expression. Okay, so this is a rational expression. And if we think back, dig into the very core of our minds from the first week of class, or maybe the second week of class, we learned how to do some multiplying and some dividing of these guys. And it all really kind of came down to these polynomials, which are in the numerator and denominator. And what we, for the most part, wound up doing was, well, we learned how to do multiplication of these guys. We learned how to do multiplication. And then anytime that we see division, we just change it to multiplication. So the first step of any division problem like this is to rewrite it as multiplication. So this is going to be multiplied by x squared plus 3x plus 2 divided by x squared minus 4. Okay, first step of any division problem is to say, ew, division is hard. I'd rather do multiplication. Okay, so now what do we want to do? Well, we have these two expressions, so we can try to just multiply straight across, but we're supposed to simplify as much as possible, okay? Which means that in the end, when we multiply across, we're going to want to have to factor and see if there's anything that we can cancel. And we can save ourselves a little bit of work, actually a lot of work, by factoring each expression right now and seeing what we can cancel. Okay, so I'm going to factor these guys. So the top on the left, let's see, x squared plus 6 minus 6. I want two numbers which add to 1, but multiply to negative 6. So I want x plus 3 and x minus 2. Then the denominator, I've got x squared plus 2x plus 1. So I want two numbers which add to positive 2 and multiply to positive 1. I think that's just x plus 1 times x plus 1. Okay, for the numerator of the right-hand side, I've got x squared plus 3x plus 2. I want two numbers which add to 3 and multiply to positive 2. We should get x plus 2 times x plus 1. And then divide. I should get, on the denominator, that's a difference of squares. So that factors as x plus 2 times x minus 2. Okay, and then the next step is, well, we can just multiply right across. So all I'm going to do is rewrite this whole jazz, except I'm going to get rid of the fractions, multiplication sign, and extend this fraction. Okay, that's just how it works. We get the denominators get multiplied, the numerators get multiplied, right? This is no different than when we want to multiply fractions like, 3/4 times 5/6, right? If we want to multiply fractions like this, all we do is we multiply straight across. So this would be like, 15 over 24, right? Just multiply the two denominators, multiply the two numerators, and make a new fraction. So that's all I'm doing here. And now I have basically, I could clean this up a little bit better. Make it like that. There we go. So this is what we got, and now we just want to cancel everything that we can cancel. So I've got an x plus 1 here that looks like it can be canceled. I've got an x minus 2, which can be canceled. I've got an x plus 2, which can be canceled. And nothing else can be canceled. So I get x plus 3 over x plus 1. And that's as simplified as it's going to get. Great. Can I upload the last two sessions on YouTube? I thought I did. But yeah, I will for sure. I think we didn't have a lecture yesterday because it was a wellness day. But maybe I did forget to upload one. Oh, wow, okay, you're right. I forgot to upload 2 in a row. What the hell? All right, I'm so sorry. Yeah, I'll get those uploaded. Stat. Sorry about that. Okay. Wow, that's really unusual. So no questions about this rational problem. Really, it just comes down to, okay, division is the same as multiplying by the reciprocal, factor, cancel everything that you can cancel. Okay, so the next one, we're supposed to simplify as much as possible. So this is going to involve all of our exponent rules. So let me just maybe take a second and remind us of what our exponent rules are. I'll write down some of the important ones anyways. X to the a times x to the b. If we take x to some power times x to some other power, we get x to the sum of those two powers. Okay, so for example, x squared times x cubed is equal to x to the fifth. It looks like a 6, but it's a 5. Okay, x to the a to the b. We multiply the powers. For example, x squared cubed equals x to the sixth. X to the a divided by x to the b is equal to x to the a minus b. For example, x squared over x cubed is equal to x to the minus 1. Well, why don't I make it 2 minus 3, which is equal to x to the minus 1, which is equal to 1 over x. Sure, we can do an example like that, Heidi. Let me get through this this problem really quick, and then we'll move on to that. Okay, so then what else do we got? Oh, if we have like x, y, z to the a, we distribute the power. X to the a, y to the a, z to the a. And x to the 1 over a is equal to the 8th root of x. And anything else? No, I think that should be good. So these are some of the rules. There are maybe a couple others that I forgot to include, but these are the most important ones for sure that we're going to need to use on this problem. Okay, so the first thing we want to do if we want to simplify this as much as possible, well, we could take kind of two routes. We could try to simplify things inside first and then apply this power 2, or we could try to distribute this power 2 onto every single y, x, and number in here. I'm going to take the approach that I'm going to simplify inside first, but that's not totally necessary. I just think it's going to save us some time. So let's see, -9 divided by 6. This is going to wind up giving me just a -3. No, -3 over 2. Right, if I divide those both by 3. Then x cubed divided by x to the power -1. The -1 comes up to the top, so we get x cubed times x to the power 1, which would just be x to the 4th on top. And then the y to the -1/2 will go down to the bottom. It'll be then, let's see, this will become, on the denominator, y to the 1/2 times y to the 1/2. We would add those powers and get y to the 1. And then this is all squared. So let's just rewrite that a little bit better than we have it written. It would be -3x to the 4 divided by 2y. And then we should square the whole thing. So I'm going to distribute the square power now onto the 3, onto the x, onto the y. So this will become -3 squared, x to the 4 squared, divided by y squared, which would just be 9. Because if I square -3, I get -3 times -3 is +9. And then x becomes to the power 8, and then divide by y to the power 2. That's my final answer. Okay, so this whole problem is just checking whether you know how to manipulate these types of expressions using these rules about exponents. When to add them, when to multiply them, when to subtract them, when to distribute. Okay, one big thing that we should never ever do is if we have a sum of things to a power a, this is not equal to just x to the power a plus y to the power a. The reason is if this a was, for example, 2, we would need to FOIL, right? We needed to do x squared plus y squared plus 2xy, right? We would need that plus 2xy here. Okay, so don't distribute powers over sums. However, we can distribute powers over products. Do not distribute powers over sums. Okay. So that's that. So that's that problem. Any questions about these exponent simplifying rules at all? Okay, if there's no problems, then I will do, as promised, the example involving amplitude, period, and phase shift of a function. So we want to identify amplitude, period, and phase shift of the function f of x is equal to, I don't know, let's do a fun one. Let's do something like tangent of x over 2. Why don't we make it x plus pi over 2 like this? Times, oh, well, this won't have a period. I mean, this won't have an amplitude. Well, I suppose we could say something about it. No, what? I changed my mind. I don't want a new tangent. We'll do cosine. Cosine of x plus pi over 2. Times 1/2. Okay, so we have here a trigonometric function, and we are tasked with identifying the amplitude of this periodic function, the period of this periodic function, and any phase shifts. Okay, so the way we're going to do this is by just identifying all of the possible shifts and stretches and compressions that we might have in this function. So first of all, I think I'm going to rewrite this. And here's the reason I'm going to rewrite this inside piece. Right now, it's sort of difficult to see what the phase shift is going to be, right? The phase shift is going to be when we have a plus or a minus of some constant on the inside. But it's a little bit trickier to see when it's kind of all written as a fraction like this. So let me just remind you of a fact, which is if I have something like a plus b over 2, this is the same as just a over 2 plus b over 2, if a and b are numbers, right? So I'm going to use this rule to split up the fraction x plus pi over 2 to be just x over 2 plus pi over 2. Okay, and now let's go ahead and identify all of the transformations that are going on with this function. So first of all, who can tell me what this purple piece is going to do for me? This purple piece out front is going to have some effect on the graph. What is this transformation going to be, which is coming from this multiplication of 1/2 out front? Sure, we can do that next, Morgan. Yeah, this is going to ultimately affect the amplitude, but what kind of transformation is it? Is it a vertical, horizontal, stretch, shift, compression? What's happening with it? What is the effect of multiplying by 1/2? Very good. This is going to give us a vertical compression, right? Or a vertical shrink by 1/2. In other words, if we were to graph this function, if we were to graph like the difference between sine x and 1/2 sine x, what do they look like? Well, they look like they go through 0 at the same points, right? The only difference is the whole wave is sort of half as tall. Okay, so it's wiggling in really the same way, but it's just half as tall. Okay? I mean, that's literally what this says. It says the height of the original function should be, if you give me an x value, you just find the sine of that value, and that's the height of the function. The second one says take the sine of that value and then multiply by 1/2. So the effect that that will have is that it will shrink our graph vertically. Okay, so that's going to give us a vertical compression. How about the next piece? How about this plus pi over 2? What's that going to give us? What is plus pi over 2 going to do to our graph? Very good. Horizontal shift to the left. And remember, horizontal shift, the fancy word we had for trigonometric functions with a horizontal shift was phase shift. Okay, phase shift. So it's going to go left by pi over 2, right? All right, and then finally we have one more transformation, which is this division by 2 on the inside. What is division by 2 on the inside going to do to the graph of this function? We divide by 2, divide our input x by 2. How is that going to affect it? Could be a horizontal compression. I think it's definitely going to be horizontal, right? Because it's something happening on the inside of the parentheses. The vertical compression and stretch happens on the outside, and the vertical like shift would happen back here, right? Something like that. So that's definitely going to be something horizontal, and the question is, should it be a compression or should it be a stretch, right? Okay, and the way that I like to remember which one it's going to be is similar to the following. So do you remember when we learned, let me just draw something to sort of demonstrate this idea. When we learned things like f of x plus a, then this was like a moves us up by a, versus if we did f of x plus a on the inside. For whatever reason, this inside thing was kind of wonky, and it seems like it would move us to the right, but it actually moves us left. Okay, so it kind of does the opposite of what we think it's going to do on the inside. A similar thing is true about the compressions and stretches. If we multiply by a on the outside, if a is bigger than 1, it's a vertical stretch. If a is less than 1, it's a vertical compression. But if we have a multiplication by a on the inside, it does change to horizontal, and it kind of flips what it is, okay? If a is larger than 1, we get a horizontal compression. And if a is less than 1, it's a horizontal stretch. Okay, so why is this confusing? This is confusing because something like 1/2 sine x has a vertical compression by 1/2, right? But sine of x over 2 has a horizontal stretch by a factor of 2. Okay, so just like how before, when we kind of know that like when we're inside the parentheses, adding something, it kind of seems like it should be moving us to the right, but it actually moves us to the left. When we have this multiplication by a number on the outside, it is going to give us that vertical stretch or compression just based on whether a is bigger or less than 1 in a kind of like intuitive way. But we got to remember that when we're on the inside of these parentheses, everything is a little bit unintuitive, and it turns out if we multiply by something which is larger than 1, we get a compression. If we multiply by something which is smaller than 1, we get a horizontal stretch. Okay, and it has to do ultimately with the question of, well, what are we affecting in our transformation, right? If we have something happening on the inside, ultimately what we are changing is the input, right? We are changing the input. Whereas if we multiply, or if we add something on the outside, this is changing the output, right? We're not messing with the input at all. Same deal with these guys. If we multiply by something on the outside, we are changing the output. Versus if we multiply by something on the inside, we're changing the input. So that's just my short reasoning as to why everything gets all wonky when we are multiplying on the inside or adding on the inside instead of multiplying or adding on the outside. Okay, so this is really the source of the wonkiness, is that it depends on whether we're changing the input or changing the output of this function. Okay, so we got to remember that when we multiply by a number on the inside, if a is less than 1, it's actually going to give us a horizontal stretch. So in this case, this x over 2 here is going to give us a horizontal stretch by 2. Horizontal stretch by 2. Okay, and now we can go ahead and and answer this question without even really having to graph this thing. We can just answer the question. Okay, so amplitude has to do with what? It has to do with the height of the wave. Amplitude has to do with height. So if we can remember what the amplitude of the cosine function is, then we can find the amplitude of this new function quite easily. Okay, so since amplitude of cosine x is 1, and f of x has the same height, but for a vertical compression by 1/2, our new amplitude is 1/2 times 1 equals 1/2. Okay, so the amplitude has to do with the height. So just giving you a visual cue for what this is. If our original cosine function looks like this, right? Our amplitude is going to be this distance from here to here, right? It's the height of the wave from sea level, which in our case is 1, right? So in this purple here, I've drawn cosine x. And 1/2 cosine x would look something more like this. And then this height here in blue is like 1/2. Okay, so that's the effect of a vertical stretch or compression on the amplitude. Okay, so next up, we're supposed to figure out what the period is. Well, the period, let me use orange. The period has to do with the distance between crests. Okay, so if we were to draw the period here in this graph, what would it look like? It would be the distance from crest to crest. Okay, so if we want to understand how this distance is going to be affected by our transformations, well, we only have two left. We've got a horizontal a horizontal stretch and a horizontal shift. Well, if we just up and move this whole thing, left and right, it's not ultimately going to affect the distance between crests. It's just going to move everything over a little bit, left and right. So the phase shift does not affect the period of this function. However, if I shrink it, okay, or stretch it in a left or right way, then it will. Okay, so period has to do with distance between crests. I will say that phase shift does not affect. Does not affect. I think I should use the a effect here because it's a verb. Or I could just say have an effect. Whatever. It's one of those. I'm a math person, not an English person. Okay, so what will affect it is the horizontal stretch. The horizontal stretch by 2 will multiply our original period by 2. Since cosine x has period 2 pi, our new period is 4 pi. Okay, so let me show you using Desmos why that's true, okay? Just check out Desmos. We'll use cosine this time. Be good. Functions. Let's have cosine x. And let's take a look at the difference between cosine x and cosine of x over 2. X divided by 2. Okay, so in green here we have our original cosine function. And then in purple, you can see our cosine of x over 2, which has been stretched by a factor of 2. And remember, our period is a measurement of the distance, okay, the distance between crests. Okay, so I can see that the first crest, if I start from 0 and I measure, I go to the right until I hit another crest on the green graph. It looks like it happens at somewhere like 6.28, right? That's 2 pi. If I go for the distance that it takes me to get from the purple 0 to the x value, which produces another crest, it's going to be more like 12 point something, right? So the distance from crest to crest has also doubled because we have stretched this whole thing out by a factor of 2. Okay, we've stretched this whole thing out by a factor of 2. Okay. So I think that's everything that we have here. We just have a, oh, well, lastly, we're supposed to say something about the phase shift. We have a phase shift. Shift to the left, pi over 2 units. So if you want to actually see what this looks like on Desmos, I can graph it for us. We can have we'll still keep our original function, and we'll do cosine of x over 2 plus, how do I even do pi on here? These functions? This? No. Oh, there it is. Plus pi over 2. And then we multiply by 1/2. Okay, so what do we get? We get a function which gets moved over pi over 2 units to the left. Pi over 2 units to the left. It also gets shifted, not shifted, stretched by a factor of 2. Okay, we get stretched by a factor of 2, and it's half as tall. Okay, so this is what our function looks like here. Okay, so who asked this question? I think it was Heidi originally. Heidi, do you feel satisfied? Yes, okay, very good. Anybody else have any questions about this example? That's good. All right, no more questions, it seems. So, Oh, there was another student who said something. I think it was Morgan. Ooh, actually, let me delete that. I want to add a page somewhere else. I'll add a page here. Yeah. Okay, so let me scroll up. Morgan's question was, can we do solution sets with inequalities? Sure, no problem. So we learned how to do all sorts of inequalities, like polynomial inequalities, or just regular inequalities, or inequalities which kind of stemmed from domain and range, and all sorts of stuff like this. So did you have a specific one that you wanted to talk about, or just you're really more interested in how do we go from something like x is less than 2 to something like x is in negative infinity comma 2, like this? Is this your question, or is it more like you'd rather solve an inequality and then give the answer in this kind of way? Both. Okay. Well then, why don't we have, let's see, last time we did some inequality, I forget what it was. Last time we did a quadratic inequality. Why don't we try doing a rational inequality this time? Those can get pretty messy. So let's try this one. Find x, find all values of x such that x squared minus 6x minus 7 divided by, so why do I make it like 3? X squared minus 9 is less than or equal to 0. How about that? Does that look hard enough, Morgan? Cool. All right, so the key thing that we maybe want to keep in mind before we start this problem is the wording of the question. It says, find all values of x. Okay, this is telling me that eventually we ought to give an interval. Okay, we ought to give an interval / intervals. Okay, find all values of x. That's kind of a cue that maybe we need to use intervals ultimately. So later on, I should have ultimately something like, I don't know, I could say x is less than 1, or x is between 2 and 3. Maybe I could say, or x is between 2 and 3, or x is larger than 4, right? I could write it something like this, or equivalently, I could write something like that as, negative infinity to 1 with a parenthesis, union 2 comma 3 with parentheses, union 4 comma infinity, right? Oh, 4 comma infinity. All right, so ultimately I want to write something like this, okay? So before we move on and solve this inequality, we should establish that we are sort of aware of how to move back and forth between these two notations here. So Morgan, do you have any questions about how I switched between these two different notations here, because they're a little bit different? You've probably seen this one more so than you have the sort of interval notation with the unions and stuff. So does that part give you any trouble? Okay, this part makes sense to you. Anyone else have trouble converting between these two notations? Okay, seems like not. So as long as we're all on the same page about that, I think we can go ahead and solve this rational inequality. And I hinted at this last time about how we would do something like this. Okay, so if I want to solve this inequality, maybe someone who was here last time could tell me what method I might use to solve this inequality. What method might I use to solve this inequality? It's one of the methods which we used to solve the quadratic inequality in class last time. Or maybe someone could just get me started on just like, how might I sort of start this problem? Yeah, we could factor for sure. I think that's a good first step. So the bottom definitely factors as like x minus 3 times x plus 3, right? Because that's a difference of squares. The numerator, I want two numbers which sum to -6 and add to -7. I'm sorry, sum to -6 and multiply to -7. I think I want x minus 7 and x plus 1 is less than or equal to 0. Okay, I think that's a great first step. It's always going to be easier to solve these things once we've got all of the polynomials factored, I think. Okay, so it doesn't look like there's anything we can really cancel. So nothing to cancel here. How do I proceed from here? How do I proceed from here? I think there's one major clue that once we've got it, we'll be able to do the rest of this problem. Okay, I'll give you guys a hint. There's one other way which we can also express these intervals here, which we have written down. We can write them down as x less than 1, 2 less than x less than 3, or x larger than 4, or we can use this interval notation. And there's one final way which we can use to express this stuff, which would be to do the following. We'd put 1, 2, 3, and 4, and then we'd use number line method. That's where I'm going with this. And then we'd use, like a circle here and draw here and nothing in between there, but a circle here and a circle here and draw in between and a circle here and draw over here, right? We want to use the number line method. Okay. Kumar, I do want to address your comment about multiplying out the denominator. That is kind of a tempting idea, isn't it? Because we could then get something which isn't a rational expression. And, the whole idea that this is a rational expression is kind of, well, it's intimidating, and it's definitely going to make things harder, right? However, if I were to try to multiply these things over here, I'd then get an inequality which just says x minus 7 times x plus 1 is less than or equal to 0, right? Because x times 0 times anything would be 0. So we'd sort of lose a little bit of information there. So that's one method that we don't want to use to solve this. So let's use the number line instead. Now, what numbers should I put on my number line, do you guys think? Yeah, thinking of something else. What numbers should we put on the number line? Yep, -1, -3, 7, and 3. Good. Oops, that should be -3, -1, 3, and 7. Okay, so I have a number line now. Now what am I supposed to do? I've got my numbers on my number line. What do I do now? Yeah, put points on each of them. In other words, choose a test point. Choose a test point from each subinterval. Choose a test point from each subinterval. Okay, the test points I'm going to pick are just, some random ones. I'm going to choose numbers which aren't too big because then it would make it kind of hard to compute. So I'll choose like -4. I'll choose -2. I always like picking 0 because 0 is usually easy to plug in. And then 4 and then 8. Okay, and what I want to do now is take each of these and plug them in and check whether our inequality is true in that region. So let's try -4. If I plug it in, I get -4 minus 7 times -4 plus 1 divided by -4 minus 3 times -4 plus 3. The numerator becomes -11 times -3. So I get 33. And then on the bottom, I get -7 times -1. So the denominator becomes 7. So this is larger than 0. And we're supposed to check whether this was less than or equal to 0. So it's not true in this region. So I'm going to mark it red. All right, now try -2. Try x equals -2. Okay, I'm just going to go ahead and plug it in. I'll get -9 times -1, so I'll get 9. Divided by the denominator would become -2 minus 3 would be -5. -2 plus 3 would be +1. So the denominator becomes -5. So this is less than or equal to 0. In fact, it's strictly less than 0. So this region is going to be a good region. So I'll mark it green. Now I'll try 0. If I plug in 0, what do I get? -7 times 1. X equals 0 gives us -7 on the top, and then -9 on the bottom. Okay, so we get just 7/9, right? Because the negatives cancel, which is a number which is larger than 0, so this region's bad. Okay, we try 4. x equals 4 gives us, well, 4 minus 7 is negative 3 times 4 plus 1 is 5, so we get negative 15 on top. On the denominator, we get 4 minus 3 is 1 times 4 plus 3 is 7, so we get 7 on the bottom. So this is less than or equal to 0, so this is a check mark. So a good region again. And then let's see here for the next one. Try x equals 8. Well, everything should be positive, right? So we'll get 1 times 9 divided by minus 3 is 5 times 11, 55, which is larger than 0, so this is a bad region again. Okay, so we've done it. Got our regions. Now, there's one final thing to take care of. Okay? The final thing to take care of is what actually happens at the values 3, 7, -1, -3. So let me write this down. I'm going to copy this and then paste. Shoot. Oh, okay. Of course, I've gotten myself into trouble. Let me add a page, and then I will paste. Okay, so finally, we need to check. We must check the actual points for circle or closed. So should we have an open circle or a closed circle? Okay, so the observation first is that x minus 7 times x plus 1 divided by x minus 3 times x plus 3 is not even defined when x equals 3 or x equals -3. The reason is because the denominator will be 0. So I must have an open circle on -3 and on 3. Non-negotiable. Because the denominator would be 0, and that would make this whole expression not defined. So forget about having a closed dot on those points, because it's just going to be, the function won't even be defined, or the expression won't even be defined. I guess it's not really a function yet. Okay, now for the other points, we just need to check individually. If we check x equals 7, we would get 0 times 8 divided by 4 times 10, which is just 0. And the question is 0 less than or equal to 0? The answer is yes. 0 is less than or equal to 0. So we're going to put a closed dot on 7, right? Closed dot on 7. And then on -1, again, you can see the numerator is going to be 0 when we plug in -1, right? And the denominator won't be 0. So again, we get a closed dot on -1. Okay. So copy this one last time. And let's actually put it in interval notation. So, final answer. Remember, my final answer is supposed to describe all of the possible x values which are in our green regions or at a pink dot, but not at these green circles, right? So let's start with the first region. The first region is x is larger than -3, but not equal to it, and less than or equal to -1. Or next region. The next region on the left-hand side, I've got a 3, and it's a closed or a open circle, so I use a less than sign, and then x, and then less than or equal to 7. And those are the two green regions, right? That's it. So I could write it like this if I wanted to, or I could say, this is answer 1. I could also say answer 2, which would be x lies in, which we also had a symbol for this. We sometimes use this symbol. X lies in -3, -1. We put a bracket on -1 because it's included. We use a parenthesis on -3 because it's not included. Union 3, 7. Bracket on the 7, parenthesis on the 3. Okay, so that's how we do this one. Kind of a long thing, but we just need to rely on our mathematical principles, okay? When we want to decide whether we should put points or circles, right? We need to go back and look at our rational expression. Imagine what is going to happen if I plug those numbers in. Will this be 0? Will it be less than or equal to 0? Will it be larger than 0? Or will it even be defined? Always have to rely back upon this expression. Okay, so that's a way that we can take one of these rational inequalities to completion. Okay, so first question, are there any questions about how I ultimately wrote down the answer? Okay, because I think some students maybe it can be difficult to go from the number line to the actual answer like one of these guys. Okay, some students don't like that process of going from the number line to this stuff. So is there any question about the notation of how I wrote that stuff down? Okay, seems like no questions. Are there any questions about how I solved this rational inequality? Okay. Rational inequalities and polynomial inequalities. We factor them and then use the test point method. Okay, factor them, write a number line, plot all the zeros, pick a test point from each interval, and check whether the inequality is satisfied. Okay, the only other way that we have of solving an inequality of like a polynomial inequality is if the inequality happens to be a quadratic, we can use the graph. But that's about it. Otherwise, we need to use this number line method and the test points. Okay. If there's no further questions on that stuff, then I will move on and talk about something new. So if anybody has another topic, feel free to shoot it out. Otherwise, I'll try one of these next problems. Okay, I'm gonna start in on the difference quotient function, but if I see something pop up in the chat, I'll divert. Okay, so we're supposed to find the difference quotient of this function, f of x equals 2x squared plus 1. I don't remember if we ever really talked about difference quotients. I think I might have mentioned what a difference quotient is at some point. In any case, all we're supposed to do is, we don't even have to worry about whether it's a difference quotient. Just find f of x plus h minus f of x divided by h. That is what a difference quotient is, but you don't really need to worry about that terminology. Okay, so, well, what am I going to do? I'm going to take x plus h, and I'm going to plug it in for x in f of x. And then I'm going to subtract. I'm going to plug in x. So I get the following. 2 times x plus h squared minus, no, plus 1, minus 2 times x squared, 2x squared, plus 1, all divided by h. Now, if I were to FOIL out the x plus h, I'd get 2x squared plus 4xh plus 2h squared plus 1 minus 2x squared minus 1, all divided by h. I can cancel a little bit of this stuff. 2x squared gets canceled, plus 1 gets canceled. I'm left with 4xh plus 2h squared divided by h. And I can cancel one factor of h from each of these terms, so I'll get 4x plus 2h, all divided by 1, which is just 4x plus 2h. So that's a simple way of solving a difference quotient. I guess what I'd really like you guys to see from this is how do we do something like f of x plus h? Well, what it means is we take the function x plus h and we plug it in for x in the other function. Okay, so the way that looked like was I took 2x squared and I replaced x by x plus h. Okay, so this is ultimately like a composition of functions where I have g of x equals x plus h, right? And then this would be f of g of x. So just a reminder about how we plug different functions into a function. We just replace the x value by that function. We need to remember to plug in with parentheses. So ultimately when we square that thing, we got to square the whole biz and use the FOIL method. Any questions about this problem? Okay, seems like not. Draw a sketch of whichever 5 you choose out of the following list of functions. Okay, Suppose we could do that. Let me draw a coordinate plane here. Come on, behave. And I'll just copy that. Paste. 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 We'll do 6. Okay, what's the first one look like? ln x looks like this. Goes through the point 1, 0. Let's see, e to the x. Looks like this. Goes through the point 0, 1. Notice these two are inverses, i.e. they're symmetric about the line y equals x. They're reflected about that line. Let's see, f of x equals absolute value of x. Well, if we take the absolute value of x, what do? We just take the x value, and if x is a positive number, then it's just x. So this is the line like y equals x. And then if it's negative x, if the x value is negative, then we take it and we make it positive. So it looks exactly the same on the left-hand side, but going up in the other direction. Here's absolute value of x. I think you guys, everybody knows what x squared looks like. Square root of x looks like this. Looks like the top half of a parabola that would be opening in this direction. Next. Let's see. I guess x cubed is the next one. We'll do that. It looks like the following. Comes up from the depths to 0, and then up like a parabola. Okay, on the bottom half, it looks like a half of a parabola which is opening down, and the top half looks like half of a parabola which is opening up. The reason that the negative side is negative is because if we take a negative number and cube it, we still get a negative number. Okay, and then we'll do this. We've done sine and cosine a billion times, so I'll just do this final one of the cube root of x. Remember, a cube root, we can take cube roots of negative numbers. So the cube root of x function is going to look a lot like the square root of x function on the right-hand side. But on the left-hand side, we're actually going to get something. Okay. And the cube root of a negative number is, of course, another negative number because we cube it and we got something negative, right? So the cube root of a negative number is also going to be negative, and this is just going to look like this. Okay, so it looks kind of like it's an odd function. Okay, it's an odd function. Okay. I think that's all we've got time for today. So next time we'll carry on and try to make it through some more of these problems. I'd recommend if you want to see a specific one of these questions done, I would maybe try it at home and then come to class and say, I want to work on number 22. And then we'll go to number 22 and work on it or something like that. Okay. Or if you have a bonus problem that looks like, you know, oh, that's so crazy hard, let's try to work on that one. Then we can do that. Okay. So any questions that you guys have, just please bring them on Monday. That'll be our last review session. And then there will be, you know, remaining review options, office hours, SI, and so on and so forth for you guys to review for the final. So hopefully you guys found this helpful. Hope you guys all have a good weekend, and I'll see you on Monday. Unless there are any further questions, in which case I can hang around after class for a couple of minutes and answer some. And Kamara will get those uploaded onto YouTube. Sorry about that. Thanks, you too.